Last lecture on magnetic field in material, we have introduced an auxiliary field called the H field. So for the magnetic field within a material is concerned, we have three vector quantities. B, the magnetic induction, which is directly measurable in experiments where the force acting on a charged particle Q moving with velocity v is given by this. Then we have magnet H field, which is given by curl of H is equal to Jc, where Jc is the conduction current density, and we have the magnetization vector M, which is the dipole moment per unit volume. Today we shall try to establish a relation between these three vectors, as we did in electrostatics, a relation between D, E and P. So this is our M. We are doing, if we take a magnetic substance, then we know that the bound atomic currents produces a dipole, which these dipoles are oriented at random due to their thermal motion. And when these dipoles are placed in a magnetic field, the torque acting on the dipole, the torque that acts on a dipole is M cross B, which tries to align the dipole in the direction of the magnetic field. So some alignment of the dipoles takes place in the direction of the applied field, and we have an induced magnetization, and M is the measure of induced magnetization. It is defined as induced dipole moment per unit volume. In general, when we apply the field, all the very small field, all the dipole do not orient themselves in the direction of the applied field, as the thermal agitation provides some opposition. So whenever we go on increasing the external field, the alignment, in general, the alignment, more and more dipole tries to align themselves in the direction of the field. So to say, we generally have the magnetization is a function of the H field. Keeping this in mind, we introduce the susceptibility first. M is a function of H. So if we write it in components, say Mx is a function of Hx, Hy and Hz. We write it in a compact way as Mi is equal to Mi function of Hj, where I is equal to 1, I and j is equal to 1 corresponds to X component, corresponds to Y component, 3 corresponds to Z component. So if we want to expression for Mx, then it is M1. When there were no field, we can expand this in a binomial Taylor series expansion like this. Mi is 0, where all field is 0. Pass. Plus higher order terms, as for example, this is for X component, this is delta Mx delta Hx times Hx, because we are expanding about the zero field case. Delta Mx delta Hy plus delta Mx delta Hz. This has been written in a compact way. If we write this approximation because we are neglecting the higher order terms. So we write it sum over j beta ij hj, where beta ij is del mi del hj evaluated with h is equal to 0. So if we found that the higher order term do not contribute significantly, we call it a linear relation. So it is a linear relation. Valid when second and higher order derivatives, such derivatives are not significant, are not if the second or higher order derivatives are important, then one must retain the higher order terms. In that case, the term will be, there will appear a term gamma jk hj hk. This is not a linear term in H. If we write this, first thing, if we consider the material, the magnetization is 0 in absence of the field, then this term is 0. But if we set this equal to 0, we exclude ferromagnetic material from our discussion, as it will appear from our forthcoming discussion that ferromagnetic material have a magnetization even in absence of magnetic field, external magnetic field. This is the molecular field that generates within the ferromagnetic material and which causes partial alignments of the dipole in the direction of the internal molecular field. So if we set this equal to 0, then ferromagnetic materials are not included in our discussion. So we write it as summation beta ij hj, not valid for ferromagnetic materials. Ferromagnets. If we write this expression explicitly, what comes out? Let me write it explicitly, then I write it for x component. So this is, on the left hand side I have mi with h. So mx is equal to beta 1 means xx hx beta xy because 1 2 hy plus beta xz hz it will be 2 1 2 for y, then beta 2 2 means and for z component this is 3 1, that is beta zx hx plus beta zy hy plus beta zz hz. We found that this is a tensorial relation, that is mx The X component of magnetization depends on the values of Hx, Hy and Hz. This is called a tensorial character, and if the off-diagonal term of the beta matrix are not zero, the material is called anisotropic. So for isotropic materials, beta ij with I not equal to j are not zero. And for isotropic material, beta ij is equal to some constant chi m times delta ij. It is a constant for all i's, same for all I. In which case this relation becomes, for isotropic material, mx is equal to chi mhx, my is equal to chi mhy, and chi mz is equal to chi maz. That is a vector. In vector form, it can be written as m is equal to chi mh, where it is a scalar for isotropic medium. Note that in general chi is a scalar, beta is a tensor having 9 components. It is a, as you will learn afterwards, it is a tensor of rank 2. But for isotropic material, it reduces to a scalar relation like this, and we call it the magnetic susceptibility. It is interesting to note the parallel definition in the case of magnetostatics. It is epsilon 0 chi E times E. The epsilon 0 appears and it is in terms of H. If we now this is chi, the susceptibility, magnetic susceptibility, this was electrical susceptibility, and this is magnetic susceptibility. So even for isotropic medium, M and H are in the same direction, and since we define B to be mu 0 times M plus H, B is also in the same direction. So we write it as mu 0 1 plus chi m h, and we introduce a quantity permeability mu 0 mu r times h, or we write it is mu times h, where we have introduced mu r relative permeability as 1 plus chi m, and absolute permeability of the system is mu r. Mu r is a dimensionless quantity, but mu have the dimension. Well, this is the relation between M, H and B. Now I come to the different types of magnetic materials. As we have introduced in the first class, that diamagnetism is a inherent property of all substance. When a magnetic field is applied, it is found that the atomic or electronic orbits gets distorted, and this gives rise to some field, this magnetization, and which is in opposition to the applied field. This phenomena was referred to as the diamagnetism. So diamagnetism is the substance in which the magnetization is entirely due to orientation. There is another type of material. This is called paramagnetic material. In paramagnetic material, there is a diamagnetic effect, but which is superseded by the orientational polarization. That is, the dipoles gets oriented in the direction of the external field, and which gives since the orientational polarization is powerful than the induced polarization, the overall effect that the field within a paramagnetic material is greater than the applied field. And there is another category of material which is called the ferromagnetic material. A popular example is iron, which is found to be magnetized or even in the absence of any external field. This is a strange class of material, and for this it is found that the susceptibility is not a constant. Let us first categorize this material. Dia, and I am first plotting the graph, which is the graph of M versus applied field H. This is MH graph. It is found that for diamagnetic material, the magnetization is in the opposition of the external applied field. So this is the MH curve. This is MH curve. Then I come to the susceptibility curve. Susceptibility as a function of H. It is found that the susceptibility is negative and it is a constant, because the slope of the image graph being a straight line, its slope is constant, and since it is in the fourth quadrant, the slope is negative. So this is the chi-MH graph. Then the thing comes how the temperature dependence. There is no temperature dependence of this. So temperature, and this is chi-M, and it is found that this is chi-M-T graph. So this is the phenomenological fact regarding diamagnetic materials. If we come to the paramagnetic material, one thing, for diamagnetic material the susceptibility is negative, so the permeability mu r is equal to 1 plus chi-m. Since it is slightly negative, it is very nearly equal to 1, slightly less than 1 for diamagnetic. Now come to the paramagnetic substance. For paramagnetic substance, as I have told, that the magnetization is in the direction of the applied field, so it is found that the susceptibility is a positive one. Chi-m as a function of And second thing is that temperature dependence of chi m. It is found that this is what the variation is chi m is 1 by T. This is known as Quivers law. So it is better to plot it in this fashion. So this is chi 1 by reciprocal of susceptibility. So 1 by chi m T graph. It is a straight line graph. And now I finally come to the ferromagnetic materials. For ferromagnetic material, it is found that the substance is magnetized even in absence of field. So this is the H, and this is magnetization. It is magnetized, it has a magnetization, and ultimately a saturation is obtained. This is called a saturation. And this part is the spontaneous magnetization. Spontaneous magnetization, that is when the field is zero, still the substance has some magnetization, and this is called a spontaneous magnetization. And if we increase the magnetic field, it is found that the magnetization increases in a non-linear manner, and you know that in this case chi has a very high value. Now if we denote the dependence of susceptibility on fields, we find initially the susceptibility increases at a high rate and reaches a maxima, and on reaching the maximum value m does not change even with the change of h. So this is the downing trend. This point is the size corresponds to the saturation. For such materials, it is found where the variation of susceptibility or reciprocal of susceptibility or with temperature, it is found that for such materials, it is found that chi m is some constant c by t minus tc. This is known as Quivers law. So if we plot 1 by chi, if we write 1 by chi or c by chi, if we write this should be t minus tc. So as per this law, the 1 by chi m must be 0 at t is equal to tc, but actually it is found that it is 0 not at tc, called the Curie temperature, but it gets slightly modified. Actually speaking, the variation that is chi m, it is found, this is phenomenological fact, that is what is obtained from experiments, that chi m varies as some constant t minus Tc to the power gamma for t greater than Tc, and this is equal to some other constant. This is some other constant to the power beta for t less than Tc. For iron, gamma is gamma is around 1.33, beta is around 0.34. So we see the variation is not very simple, and furthermore T is equal to 1093 Kelvin and Tc prime is equal to 1043 Kelvin. Generally this is called the Curie temperature. The interesting thing about is that the substance, this ferromagnetic substance, behaves as ferromagnetic for temperature less than critical temperature or the Curie temperature, and above the Curie temperature the material becomes paramagnetic. That is apparent from that at high temperature this graph is straight line graph, which is the characteristics of paramagnetic materials. At the Curie temperature, there is a soft transition takes place between the ferromagnetic and paramagnetic states. You will learn in detail about this ferromagnetism in solid state physics course. Now another interesting thing about the ferromagnetic material that its susceptibility depends on field. It has a high value of susceptibility. Furthermore, the state of magnetization depends on history. Let me explain this fact through the popular curve known as hysteresis curve. Consider a ferromagnetic material. I am taking the example as with ferromagnet because they are most popular. So we consider a ferromagnetic material, say a material in the form of a long rod, and we wrap wire around it. So a current flows, steady current flows, I current flows. So this behaves as a solenoid. So the field, H field within the solenoid will be in time sign. It is an infinite solenoid. So this is the, so you may consider the independent variable is as either H or I. So we first go to the MI or MH curve. Say by somehow we get a magnetic material or ferromagnetic material which was not magnetized at all. This can be achieved. I will come to this one afterwards. Say we call it I and this is M, magnetization. If we go on increasing magnetization, it will come and ultimately it will attain the saturation. So this corresponding field is known as the saturating field. If we now increase the decrease magnetic field we will find the curve traces this path. When I becomes 0, that is current becomes 0, the field, the magnetization does not go to 0 but has a non-zero value. This is called retentivity, and this is the retentive magnetic field. This is the retentivity. It is the capacity or capacity of the material to retain its magnetism even when the magnetizing field has been withdrawn. So this is the retentivity. Then if we go on decreasing the field down to 0, we say that when we reverse the direction of the field, we will reach a point where the magnetization will be 0, and this amount of current or H field is needed to make the remnant magnetism 0. This is called coercivity. And if we go on increasing the field in the negative direction, we will achieve a saturation in the negative direction when all the dipoles, in this case if all the dipoles were aligned on the right, on the up, then here all the dipoles are aligned in downward direction. And if we now go on increasing the field, we will see that this is the nature. So at 0 field, there are 3 values of magnetization: this much, this, and this. Now, what will be the value of magnetization at a particular H field depends on the state of previous history of magnetization. That is to say, the ferromagnetic material do possess a history, and this curve is known as hysteresis curve. It is either MH curve or MI curve, but popularly by hysteresis curve we mean a curve between B and H. This is BH hysteresis curve, or most popularly by hysteresis curve we mean this one. This is the BH hysteresis curve, and here the difference is that we define B as mu 0 m plus mu 0 h. At this point, m comes to a saturation, so the curve will be horizontal even if we increase h. But here, even at the saturation point, this part becomes a stationary, but this has a linear relation. So the curve doesn't have any, BH hysteresis curve doesn't have any saturation, but here they increase linearly. This is the main difference. Otherwise, this is a measure of retentivity, this is a measure of coercivity, etc. And the area under the BH curve, the area under the curve is a measure of the loss per cycle. Energy loss per cycle. That is, if we keep on magnetizing and demagnetizing, or subject a ferromagnetic material in a cyclic process of magnetization and demagnetization. This part if we call magnetization, this is obviously demagnetization, but then some energy is lost because this movement of the movement of the dipoles is not a reversible process. So the energy loss in the irreversible process appears as heat, and when we take a ferromagnetic material and subject it into the several cyclic process, then we find that the material gets heated. So the area under the curve is a measure of energy loss per cycle, and since it is directly related to the loss of energy, this curve is very popular. If we want to have a magnet, permanent magnet, then the permanent magnet should have a high value of retentivity. So this part is used a material which has a high retentivity is used as permanent magnet. On the other hand, if you want to have an electromagnet, so that the field goes to zero very fastly, the retentivity goes to zero fastly as H is removed, then we should have a material with low retentivity. And lastly, what I want to say, how to get this point, that is how to set a ferromagnetic material in a state which doesn't have any magnetization in absence of field, because in a laboratory we frequently need to use ferromagnetic material and put it in a cyclic magnetization. Say we have a ferromagnetic material, and initially due to time its magnetization becomes zero, and when we magnetize it is the cycle. This magnetization H is proportional to I. If we do this thing, if we gradually go on increasing I, then the curve that will be thrust out is like this. And ultimately, if you go on increasing a decreasing current, the smaller and smaller hysteresis loop will be obtained, and finally we will reach at a condition when the retentivity goes to zero. This is the proper way of demagnetizing the ferromagnetic materials. By this, we end our discussion on magnetic fields in materials.